Right. Thank you, Peter, and thank you everyone for here, and thank you to FTASA for the opportunity to take part in this symposium over the next 2 days. Already we've heard about the processes in soils and the development of soils, and the process I'm talking about, soil acidity, is one that is very much accelerated by agriculture. I want to talk about a journey that really takes the time that I've been in the department to try and promote and encourage the care and treatment of our soils. Just quickly though, I thought I'd just introduce Western Australia and just try and put it in a little bit of context. We have 2.5 million square kilometres and 2.6 million people, so they've nearly got a square kilometre each. However, the people are mainly concentrated around Perth. It has nearly 2 million of those people, a few cities around the coast, and most of the area that I work for is that dark orange colour, which is called our grain belt. Just magnifying up that area a little bit, we can see that from the black arrows on there are showing a decline in rainfall and a movement in that reduction down towards the southwest. Our rainfall comes from the southeast, but it's declining from this way. This rainfall line here is about 225 millimetres of growing season rainfall, and in the upper end of the wheat belt here is about 450 millimetres of growing season rainfall. Obviously that has some fairly significant variation from year to year. Wheat is our dominant crop by far, with others in there and a reduced amount of pastures. We used to be considered a wheat sheep sort of agriculture, but sheep are much reduced activity. Listening to the previous speaker talk about soil types, this map just gives the dominant soil type in each of those areas across the regions. They joke that we've got 15 different types of sand, so we're a little bit generous when we go to the loams and the clays. We still have very light textured soils. The key feature that you'll see, dominated by sands, deep sands in the northern area, duplex soils, which means sand 10 to 50 centimetres over a clay layer. This will come up in the talk a little bit later on. And then mostly forest gravels through this region, and that is still quite a bit of forest, so not quite so much agriculture in there. So why have we developed acidity? Agriculture's about 80 to 100 years old across most of the wheat belt. There was a rapid expansion, and our yields sat at around about 1 tonne to the hectare in terms of wheat as a rolling average. From about the 1980s, there were many activities introduced and changes to the farming systems that are all listed on the chart there. And that led to a rapid, over the next 20 years or so, increase in average yield up to about almost a doubling. A lot of that came from increase in the use of nitrogen fertilisers rather than a wheat clover rotation with the sheep. We were going into more and more cropping, and more of the fertiliser came from nitrogen fertilisers that was applied. Unfortunately, at the same time, the amount of lime that was applied didn't increase, and therefore we had acidification of the soil profile. The main processes that contribute to that acidification are similar to what we heard about in the previous talk. They're just accelerated in this system, so we're getting an application of ammonium-based fertilisers, and there's the processes that go through there, including the leaching of the nitrate, if that's used inefficiently, adds to acidity in the soil profile. And then the main reason for the farming is to do with export of either grain, sheep, or meat, or wool, or hay as well. Anything that we remove from the farm, being organic origin, being plants and animals, is slightly alkaline in nature, and that means that we are removing that from the farm. If we're not replacing it essentially with lime, then we are leaving more acidity behind in the profile. This is a picture that shows, some of you may have seen before, that just shows what we've been able to do over about 50 or 60 years of farming of this particular site. So our soil is ancient and weathered, so it already starts off being acidic at around pH 5. And this, I'm just make a point here of saying that we measure pH and aluminium in 0.01 molar calcium chloride. which is reasonably equivalent, I think, to your stronger potassium chloride, and about 0.7 of a unit, pH is about 0.7 of a unit lower than if you were measuring in a water solution, a water extract. So as I said, we've got a natural profile, which is reasonable for agriculture, a deep sand with, in the subsurface here, of about 8% to maybe 12% clay. And what we've been able to do with agriculture, without applying lime, is firstly compact an area down here to about 30 centimetres, which you can see by that blocky appearance. But we've reduced the pH by over a unit down to about 3.9. What that means in our soils is that we get an increase in aluminium that's in the soil solution, and that is toxic to plant roots. And my whole story revolves around removing that aluminium toxicity to allow roots to grow deeper into the profile to access moisture and nutrients. I think that's the overriding factor that we're looking at in terms of managing acidity. So on the pictures there, courtesy of CSIRO, show a healthy root tip and one that has been impacted on by toxic aluminium in the soil, upsetting the cell division at the root tip, leading to short and stubby roots, which you will see on the next slide here. A slide that was produced by a colleague of mine during his PhD. That is wheat plants grown in increasing aluminium sandy soil, just by mixing two different soils to vary the proportions. That's what happens to the roots at high aluminium levels, very short roots, when they hit that aluminium layer that I showed in the previous picture. In the topsoils, there are different concerns about low pH, and they revolve around nutrient availability. So essentially we would like pH to be somewhere above 5.5 and up to maybe 6.5 or 7, although that's quite difficult to achieve. And then the other major impact that we have in the topsoil from low pH is the effectiveness of the legume nodulation, the rhizobium symbiosis. And there's been some pretty significant work developed in Western Australia with ceredellas and other legumes that have a symbiosis that's much more adapted to acidic soils as a pasture legume. So that's by way of introduction. We knew what the causes were, we knew what was happening, and we're seeing that we could fix that with our low buffered soils with an application of around about 3 tonnes of lime at a 70% neutralising value would overcome the problems that we've developed and be able to, as a 1 to 2 tonnes every year, or every 10 years, sorry, would probably manage our sort of pH profiles and eliminate acidity as being a problem. We had lots of evidence from trials just showing that, that there were many trials done. We had many responses, big plants, little plants, to do with liming that showed that this was a thing that should be done. A lot of these results were coming from very acidic sites that we did the lime trials on, and we were trying to tell the message to farmers, and this is probably one that I've learned over the years. Put some more lime on, or put lime on now, start putting lime on before soil acidity becomes a problem on your farm, and it will maintain the soil and you'll maintain your yields. So it was an extra cost for no extra perceived benefit, and it was not a successful message, as you might imagine. We started to show additional benefits of applying lime and managing the soil pH, and this slide shows that we looked at barley yields on a long-term site that had been limed, and this is 18 years after it was the original application. So we had a fixed profile, if you like, or an ameliorated profile and an acidic profile. And you can see that we had much more barley, much more competitive on the ryegrass yields here. So ryegrass was much more limited, a very stressed barley crop where the weeds took off. And this was another aspect that started to trigger people's thinking that there was more to just managing soil pH and getting extra yield. Obviously we're blessed, I guess, with lime suppliers, and there's a joke when I talk to lime suppliers here that our lime suppliers are not actually miners, they're just loaders. This is the mobile sand dunes, which is between 85 and 95% pure calcium carbonate. Mobile sand dunes, unvegetated, that exist on the coast up north of Perth. They literally just pick it up in a loader and put it in a truck and take it to the farms. It's a lime source that's about all less than 0.5 of a millimetre. We don't have any of the microfine product in it, but it sells for between 80 and 100 rand per tonne at the pit. Further south of Perth, we have soft limestone sources that have been settled or compacted for a bit longer than the mobile dunes. There's still, the source, the origin is limestone, seashells and coral that's been broken up by the ocean. This is just basically minimal processing on these sources as well. So obviously that wasn't working. We needed to raise awareness, and we set out to do this by, so we're talking sort of 10 or 15 years down the track. The soils have continued to acidify, and we had a joint project with Precision Soil Tech, a commercial soil sampling company, with funds where we used farmer funds and project funds to actually access over a period of 6 years almost 100,000 sites across the wheat belt. We were able to look at pH in the top 10, 20 and 30 centimetres, and as a result of that we could produce maps that showed 3/4 of our topsoil samples were below the pH target where we would like them to be. That's above 5.5, and the reason for that is that we want lime to move down through the profile. If you have pH lower than that, then any lime that dissolves is used up managing or treating pH in that surface layer. So we want it to move down through the profile to treat the subsurface layer. This is the pH pH risk map that we were able to prepare. So this is done in collaboration with the department's soil type mapping. We were able to look at the 10 to 20 centimetre layer, and for the first time show that nearly half of the samples that we were collecting from these soils were below our recommended target of 4.8. Now we chose 4.8 because we wanted to avoid farmers decreasing their pH further in the subsurface layer to 4.5, where at 4.5 the level of aluminium increases exponentially, and obviously with the pH being a log scale, it's much more difficult to fix going from pH 4.5 than if you started some action when it got to 4.8. So that's the ideal. And if you look at the 20 to 30 centimetre map that we were able to draw from this process of having the tens of thousands of samples to put in, you can start to see some regional differences. And this is that duplex soil where we're hitting a clay layer down in the lakes area. pH not so low in the subsurface there, but in those deep sands that I pointed out, we're getting much more proportion of lower pH soils in those deep sands. And you'll see in a moment sort of what the impact of that is. But just going back to this awareness raising program, what we did was talk to grower groups, get people involved, and we were able to talk to 600 directly sample 600 farmers over a 6-year period. And for each of those people that were sampled, they belonged to a grower group, and we were able to run 3 workshops with each of those groups. So an initial one, a results one, and a follow-up to see what they're doing. It was either in the field or in the sheds. We were able to talk directly, so we sampled 600 people, but we're able to actually interact and talk with half of the growers that manage that 17 or 18 million hectares. There's about 4,200 commercial farmers that manage that area. I guess one of the pleasing results, it's always good to be able to show that some of these project activities have had an impact. The grey arrows on this chart show the project years, where obviously we were encouraging people and assisting them with the deeper soil sampling, so you'd expect an improvement. But in the 6 years since this project, this chart shows the proportion of samples from 10 to 20 and 20 to 30 in the blue colours that are sampled as a proportion of the topsoil samples that are currently sampled. So we're at about 60 to 70% of every topsoil sample that gets collected has those deeper soil samples collected. And what we're also seeing without project input is that the even deeper layers to 30 and 40 and 40 and 50 centimetres are now being sampled on the sandy soils. So this knowledge that people have now got about what their soil profile is and their consultants have got is what Peter was talking about, is that significant improvement over the last 20 years in the application of lime. So not only has the rate increased, but also the area that's being applied has increased dramatically. It's been a little bit static for the last 2 or 3 years, and that's had seasonal influences to make just to reduce something. We had a very wet summer, which meant that trucks couldn't actually go onto the paddocks to deliver the lime, which reduced sales quite significantly in 1 year. Just going to go through these next slides very quickly and to show what could be possible if you can start liming before acidity becomes a significant problem. And it was still an issue, but it was not too significant at this site. It's a small catchment, 22,000 hectares and a few farmers, and we sampled in 99, 2006 and 2016. Those are the individual samples, just colour-coded. Basically pink is bad and green is good. That's in the first year, 1999. 7 years later, after they'd had the input and the discussions with them, more green dots obviously, and then a further 10 years later when we were able to go back and sample those same sites again, the majority of the sites have reached the pH targets that we're chasing. The next slide just shows what happens for the next layer deeper down. So more sites didn't meet the profile, didn't meet the targets. Then 7 years later, a few were starting to, and 10 years, some have and some have still got some way to go. So that's just a nice longitudinal study over a significant period of time. What it shows, and this chart just says that if we keep on the trends that we're going, then we should reach in that catchment about 80% of the soils reaching the targets by 2020, which now is only next year. So I think it's another good example where it's worthwhile getting started early on. So what has happened where farmers have put all of that lime on? They've increased their rate. Some have now applied 4 to 6 tonnes of lime per hectare in the last 4 or 5 years, maybe 6 years. And we are getting a significant banding of lime. I'm not sure if you can sort of see that here, but the topsoil that has had lime applied to it has turned purple when stained with universal pH indicator. I should have mentioned that in those earlier photographs. I was using universal pH indicator, which changes from orange in acidic to purple in alkaline, green for about the mid-range. So this has been sprayed, just gives us an indication that there's undissolved lime in that topsoil. We've put plenty of lime on and it's just been, I guess, sitting there. It's changed pH in the surface. There's no more acidity in the profile or in that area of the soil. So it's very little dissolving, very little movement in our no-till systems. And we've got now an alkaline or a high pH topsoil over a very acidic subsoil. So this has become a problem that we really have to try and address through our research. And that research is now aimed at mixing the lime that has already been applied or any that we do apply through the profile. And the top picture over there shows a patchwork of dark and light bits, which the light bits are the acidic soil. This is a profile that has been spaded, so it's one of our soil mixing strategic implements for doing a mix. We've been 25 years in a no-till system, and a number of problems have developed, including water repellents on the surface here. So this is water-stained purple that just is not flowing into the profile. Eventually it will move in through different zones, but large areas of the soil actually remain dry, sometimes right through our winter growing period because of this hydrophobicity of the soil. And the other obvious one that without controlled traffic in the system, we get quite serious compaction layers, and they've been developing deeper and deeper the larger our machinery has got. The other one I've already mentioned is the herbicide weed resistance, that we get a build-up of weed seeds on the surface, and weed seed bank. Often many of those seeds are resistant to herbicides, and so another opportunity with some strategic tillage is to bury those seeds and remove them and take them out of the equation for farmers. Another driver for this research and the acceptance of some sort of tillage system is that you can see on the map here, any of the dark purple colours show that 50 to 100% of our soils have more than one or more than two soil constraints, significant soil constraints at the same time. On the profile there, we have water repellents in the surface, we have soil acidity problem in the subsurface, and we've got a deeper compaction layer with high soil strength as a result of trafficking. This profile, those measurements came from this profile before it had a disturbance introduced to it. As is often the case, farmers are very quick to see an opportunity and start applying it, and often without what I would consider enough scientific background or scientific validation. So they're getting out there and having a go. Field days where various types of soil tillage equipment is being demonstrated, such as a deep ripping tine down to 550 millimetres with opener plates on here, plates that are designed to allow more soil from the surface to fall down in a seam, a rotary spader system, the old moorboard plough, which completely inverts the whole profile, and modified one-way ploughs, which throw the soil around a little bit more than what the traditional one-way plough does. So field days like this regularly attract 200, 250 people to have a look at it and see what's going on, and they rush out to see if they can achieve some of the soil disturbance to try and get the aim of things I've been talking about. However, I think there's an opportunity, and our research focus now is on trying to make these, give some guidance about which soils and which tillage mechanisms should be used, how to maintain the benefits from those tillage treatments, mostly through controlled traffic, but there's also application of organic material if possible, if available, to help preserve some of these improvements that we make from this significant intervention. There's an opportunity to try and get them to avoid this, for example, where this site has been moldboard ploughed, the limed topsoil has been placed at depth, we've turned up a very acidic subsoil. They tried putting a little bit of lime on the surface. You can see it's just stained purple right in the surface. But this plant is essentially growing in one of those subsurface acidity soils, and it's not doing very well at all. A better result, but perhaps not influencing enough of the soil profile, is the deep ripper with the opening plates that allows lime topsoil to move down in a slot. But again, and we can see roots that do grow through and follow that down, we don't think we're getting enough of the profile treated in order to maximise our growth. We've got a situation where roots grow in that seam, and at the end of the season, when the temperature heats up, we're not getting enough water inflow into that seam to feed those roots, and we certainly don't get the roots growing out into that aluminium toxic soil. We've got work here with the big tubs looking at just how much of that soil does need to be ameliorated in terms of the seams, and also looking at column work, looking at movement of lime under different rainfall regimes and different levels of lime going on. We've also had an interest in looking at alternative limes. So I showed you those big bulk lime sources that we've got, but there are people that are promoting prilled lime that can go in with the seeding equipment at much lower levels. We have liquid lime, which is fine calcium carbonate in suspension, again, that can be drilled into the row and combat existing or ongoing acidification rather than the existing ones. What we're seeing, interestingly, in the prilled lime system, it's been placed into pots and then washed out, is that we can still find the prills because they've had soil around them, so they haven't been able to disperse in the soil. We get a proliferation of roots that around each of those prills, and you can see there. So we do get a small benefit, but we're not being able to treat the bulk of the soil profile with that system. This apparatus and setup with large soil pots with the banded seams in, we've been able to look at the root growth shown on these charts here. If we have no seams in the soil, we get a limited root growth out of the topsoil. We get nothing into the deeper profile of the tubs. If we put a slot in between the rows, trying to sort of maximise the access of different rows to those treated slots, we get a medium increase in the amount of roots, and we get roots penetrating into the soil deeper below. But if we can actually treat the soil directly underneath the rows, then we get a much bigger benefit in terms of the roots going deeper down through the profile. Probably related to time and also just the amount of roots going through. We've done field experiments to actually find out if we do, and if we are able to fully treat the profile, then by removing compaction and acidity in this particular site, we took out the soil layer by layer in a trench, applied lime at various treatment plots across that trench, and reincorporated the soil back in, so that we had a series of treatments that led to a control, a situation without compaction, and then the other treatments of lime at different depths. You can clearly see the benefit of just removing compaction in the layer here where my colleague Gazey is standing. The compaction gave us removing compaction gave us a significant response compared to the controlled pots. In the control pots, roots only grew down to 25 centimetres, so we were able to put cameras in underneath and measure where they were growing to. It's quite an acidic profile, 3.9. Where there was no compaction, what surprised us is we did get roots down to about 50 or 55 centimetres. They were very coarse roots. There were no fine roots that we saw where we'd got rid of compaction and got rid of acidity. And so there was a response to this in terms of the water that they could access. But water and nutrients in the plus lime treatment gave a greater response. But I think that's just a testament to how well our wheat breeders have got at breeding tolerant crops, and that's been one of the drivers that farmers have been able to increase their levels of acidity, or let the soils become more acidic, but still be profitable because of the tolerance that the crops have to acidity. So obviously, as we've added lime at the different depths, that chart shows that we've increased pH. This point here looks a little bit out. It was just to do with the depths of where those rotary hose, when they were putting in. So we had in the samples, we had a slight lower pH in that zone. If I add on there, obviously when we raise pH, we decrease aluminium, remove that toxicity, and allow the root growth through the profile. That resulted in yield going from about 1.5 tonnes to 3 tonnes, and as I said, there was a significant increase to the excavation or removing the compaction in the first year. What we expect, as we put other crops on there as well, such as a barley or canola that is less tolerant to acidity, is that the ones with the additional lime treatments down the profile will continue to stand out, and our experience would say that a profile altered like this, as long as we don't recompact it, will last for 10 or 15 years. What's particularly interesting to growers is that we've been able to increase the water use efficiency. Obviously all the plots there receive the same water. We're growing much more yield from the same amount of water. Farmers use this water use efficiency, a modified equation to say how many kilograms of grain are they able to achieve per millimetre of rainfall. And that's quite a significant jump. 24 is quite a significant number. This is some data from one of our larger consulting groups. They put a summary together of all of their clients, and their bottom 25 clients get about 8 kilograms per millimetre of water and make about $100 a hectare profit. They're good farmers that adopt all of these practices that I've been talking about, and probably some other practices as well in terms of their timing and everything else, because they do the whole system farming, able to increase that water use efficiency by twice. But the important thing is, and that's including adding in the lime and the other soil practices that they do, they're able to increase their per hectare profitability by more than 3 times. And I think it's these sort of numbers that we're being able to show people that's now making it worthwhile to treat this problem. So where does that leave us now? You know, we know we can do it with tillage. We know that tillage can treat multiple constraints all at once, but we're actually doing all of the things that we stopped doing when we went to no-till, for obvious reasons. We're leaving the soil bare and exposed to erosion. We're churning in the organic matter that's been accumulating, which mineralises a lot of it and sometimes gives us a good response. Sometimes it just means we lose more nutrients out of the profile. So how can we maybe look at doing something that doesn't require the strategic tillage, particularly if we don't have the other constraints that I've spoken about? So back in 2000, we started doing some lime injection work with an apparatus that we put together, and not being engineers, we were able to make some pretty fundamental mistakes and inject the lime to the bottom of the hole, leaving an acidic profile in between. So an expensive lime and operation, but no result. On the other hand, it's a little bit harder to see on this photograph, but we were able to get a more dispersed incorporation of lime and into the profile, but we weren't able to control it or control the distribution very well. So what we had was lime here in too much. It's been stained purple, so there's too much there, more than we need. And this photograph is actually taken 15 years after we injected the lime in. So we've got still a good pH profile there, but within that area there where we injected too much lime, blowing that up to here, we've got undissolved lime particles, lime grains, that are just sitting there. They're not returning any benefit to the farmer. They're not changing pH anymore because it's already been changed. So we're looking for a system and an opportunity to maybe still inject lime to treat these sort of profiles. So we've got an acidic profile here. As I said, the farmer has put plenty of lime on the surface, and we've got an area from about 20 down to 70 centimetres that is compacted and low pH, stained in that orange colour. If we could get roots to grow through that in an effective way, then we are liberating from 0.7 down to 1.8 metres of good sandy soil in a good pH, not compacted, and wheat roots will easily grow down to 2 metres in our environment over the season, accessing water. When the farmer dug this hole for us, he was so surprised that he carried on digging, which is why it's as deep as it is. But from about 30 centimetres or so, this soil was actually wet, and he'd already harvested his wheat crop. And that's a real eye-opener, and that we have a lot of this sandy soil in this condition that we're wanting to look at and try and treat. And that's one of the reasons why I'm here. While I'm here is to talk with some people who've been building a lime injector applicator here. I'd like to thank you for your attention. I'd like to thank Fatasa and Peter again very much for the opportunity to be here, and I'm looking forward to the discussions. I have to thank the many colleagues that I've talked about, lots and lots of work there, and the interaction with lots and lots of growers, and also our funding body. There's a long list of people that's been involved over the years. Thank you.